Hi, this is an example problem from Chapter 11 on fluid flow. This involves Bernoulli's equation and the equation of continuity. Pause for a moment and read the question. So in this problem, we're looking at how fluid flows through a pipe that undergoes changes in its height and in its diameter or cross-sectional area. We're going to be using a couple ideas to understand and solve this problem. One is the equation of continuity, which we've seen before. The volume flow rate at any cross-section of the pipe has got to be the same. Same amount of volume of fluid flows through the pipe. If it didn't, the pipe would burst or you'd have air pockets. So that's not going to happen. And that tells us that at any 2 points in the pipe, the A times V is equal. So we're going to write that one down here. So we have the equation of continuity at point, so here's a point 2 to point 1, for example, right? We can say A1, V1, that's the volume flow rate there. It's got to be the same at A2, V2, so with that cross-sectional area and that speed. Second one we're going to use is Bernoulli's equation. Bernoulli's equation is a lot like, it looks like an equation for conservation mechanical energy. We've got pressure term, we've got a term that looks like kinetic energy except for mass you have density, and a term that looks like potential energy but instead of mass you have density as well. And this is written in a way that we have a certain sum of these three terms at one point, and when we add them up at any other point, although the individual p, v, and y values may change, the sum of those three will be the same as it was at any other location. That is Bernoulli's equation. So let's go ahead and write that one down. So there's Bernoulli's equation. And let's go ahead and label these just for a second so we remember what these are called. All right, so here we go. Now, the way that we solve a problem like this is both of these two equations can be used together because they contain similar variables. So for example, we've got V's, right? In both these equations. We've also got so that's the variable that unites the two equations. We've also got a height. We've also got cross-sectional areas. And we've also got pressures, right? So at every one of these points, one or two, we can look for these four variables. In this problem, we are going to be on the first floor and have a certain pressure and speed. So we've called point 2 down here. This is point 2 on the first floor. And here we have a value of the pressure, which is equal to 3.4 times 10 to the 5th pascals. And we have a speed here on the first floor, which is equal to 2.1 meters per second. We've also got some area there. I'm going to call this again 0.2, right? We don't know what that is per se. And we also have some height y. And we don't know what y2 is either, per se, here. Now, let's look at point 1. Point 1, we are up here, and we've got a height which is 4 meters greater, right? So if I want, I can call this position here. Let's go ahead and make a little line right here, right through. Let's call this one y2 equals 0 here. And y1 in that case, y1 is equal to 4 meters. Again, I'm just setting my reference point like we did with conservation mechanical energy. So we've got that. And then the speed we can see also here. This guy right here, it's equal to 3.7 meters per second, which according to the equation of continuity means that the pipe must have narrowed a little bit in order for the speed to increase with a smaller diameter. Now the question we have here is, What is the gauge pressure of the water on the second floor? So we don't know what this is. What is this pressure up here on the second floor? We're going to try to calculate that. This is what we're looking for. So looks like we can definitely use Bernoulli's equation because we're dealing with water. So we know what the water density is. Density of the fluid rho, 1,000 kilograms per meter cubed. We know that y2 here is equal to 0, so this whole term is going to be gone. We know both the speeds, so those are known. And we also know what the pressure 2 is. So let's go ahead and put these values in, or clean this equation up for a second. So the pressure on the second story, P1, I'm going to subtract the things we don't want from the this side. So right now we've got 1/2 rho V2 squared, and that's forgot to have a P in there. Let's move that over real quick. And we have a P2 already. And then we have a 0, right? So that's just this side of the equation. And then finally, let me subtract the other term. So minus 1/2 rho V1 squared minus, that took care of that, rho G Y1, that took care of that. And I think here that we do have all the values that we need. We do, so we can plug in and solve for the pressure here. So P1 is going to be equal to P2, which we know here, 3.4 times 10 to the 5th pascals, plus 1/2 rho is 1,000 kilograms per meter cubed, density of fresh water, multiplied by V2 here, 2.1 meters per second squared. Then we're going to subtract from that 1/2 rho, again, same fresh water, multiplied by, we're looking at in this case, V1, here it is. And so that's going to be 3.7 meters per second squared. And finally, we need to subtract off the rho gy. Again, 1,000 kilograms meter cubed for fresh water, multiplied by G, 9.8 meters per second squared, multiplied by Y1. Here it is, 4 meters. Putting all those numbers in, we are going to go ahead and get an answer for the pressure at the top. That is equal to 2.96 times 10 to the 5th Pascal. All right, let's analyze this result for a second here. So the pressure down at the lower story, 3.4 times 10 to the 5th Pascal, is greater than the pressure here, 2.96 over at the top story. And that makes sense because we had to do a couple things. We had to move the water uphill to the second story. That requires a greater pressure below to push it up. But not only did we move it up, we also increased the speed from 2.1 meters per second in the lower story up to 3.7 meters per second in the upper story. And that also requires a greater pressure below. So what we're doing here is we're moving the water up and we're speeding it up. The pressure below has got to be greater than it is at the top in order to push that water up and speed it up. General commented about this type of problem. Anytime we have fluid flow in a tube that may change height, that may change diameter, we can always apply the equation of continuity and Bernoulli's equation. Together, they both explain the phenomenon. And notice that equation of continuity and Bernoulli's equation each have speed in it, the fluid speed. So if you solve for V in one, you can always plug it into the other equation. In this particular example, we didn't have to do that, but in general, that's a good method for solving problems depending on what information you have. There's always 4 variables, and you want to try to figure out how to answer the ones that you don't know using these 2 equations.